Actually, I'm talking about exospheres of Mercury and the Moon. So I thought since they're a little bit similar that I would talk about both. So I'm going to start just with a tutorial, then I'll talk about extreme volatiles, which are like hydrogen and helium, then the refractories, and then unresolved questions. Why we didn't see oxygen by messenger, important mechanisms are controversial. The neon densities that were reported vary by 2 orders of magnitude. What's the role of surface composition? What are the bright coronae about hollows? Are there sulfur? And I'm going to talk about some seeing effects on ground-based observations. So to begin with, what is an exosphere? It's a collisionless atmosphere. So the atoms, when they escape the surface or the atmosphere, if it's an exosphere bounded by an atmosphere, they're more likely to return to the surface than they are to impact another atom. So it's almost like if you were here on the Earth, you would call it a perfect vacuum. So where are exospheres found? Well, a collisionless extension of an atmosphere is an exosphere. The Earth's atmosphere has an exosphere above it. Or in the case of the Moon and Mercury, the exosphere is the tenuous gas above the surface, and that's called a surface-bounded exosphere. And so the little cartoon at the bottom was taken from a paper by Smith and Marconi. They wrote it in 1995, but it's a very good tutorial that I think every student of the subject should read. And it shows that the source atoms can either follow a ballistic orbit or an escape. At the Moon and Mercury, although for an exosphere whose bound is an atmosphere, you have orbiting atoms, but for the Moon and Mercury, the orbitals are not allowed. So you see the little simulations on the right show the lunar sodium and the lunar potassium, and the reason they're different is because the difference is in radiation pressure. So what are the sources? Thermal desorption, impact vaporization, photon-stimulated desorption, sputtering, diffusion from the interior, volcanic activity, or in the case of the Moon, is possibly rocket exhaust. And one of our young scientist, Parvati Prem, has done a simulation of what will happen with the rocket exhaust and where it goes and how long it takes to dissipate. So the sinks are either escape if the atom has velocity greater than escape velocity, or it can re-impact the surface and it can either bounce or stick. Ultimately, it might find its way to a cold trap, or it might diffuse into the regolith. So why are the sources difficult to quantify? Well, thermal desorption, the question is always, are the atoms thermally accommodated to the surface? And we still don't know that. Impact vaporization, you have to know the impacting flux, you have to know the velocity distribution of the impactors, you have to know the density and porosity of the impacting dust or meteor. For photon stimulated desorption, one thing that really hasn't been considered but should be is what is the effect of shadowing? You have micro shadows. What's the velocity distribution of the ejecta? What's the cross section for PSD? And surprisingly enough, there's an order of magnitude difference between the cross sections that have been used. And the same is true of sputter. I've been working a lot on sputter recently, and the sputter yield is really not well known, especially for sodium, because you have to know the surface binding energy, but how to define that surface binding energy if you're talking about a mineral, you know, that really isn't well known. And what is the sputter velocity distribution? You would just be amazed at the different distributions that have been used. And you can see here, this is from a paper by Carl Schmidt. And you can see for the sputter velocity distributions, the ones labeled here 3 and 4, they're enormously different. And that's because the binding energy that they've used, of course, is quite different. The peak of the distribution is the binding half the binding energy. And so the binding energy that you assume is very critical to the velocity distribution. And of course, the vertical dashed line here shows you the escape speed for Mercury. For the moon, it would be 2.25. So the atoms that are above escape speed are going to escape, and the others are going to re-impact the surface. So all of these different distributions are, you know, very controversial. You can look at micrometeor impact vaporization, the blue. Some people think that the velocity would be thermal at 2,500 Kelvin. People have used temperatures up to 4,500. So there's a huge difference. And that makes a whole lot of difference in the fraction that escapes, how far the atoms go, where they land, how long it takes for them to get to the cold traps, and so on and so forth. What do we know about hydrogen at Mercury? Well, you can see the blue curve, the blue solid circles, and our fit. That was from Messenger, and the red or orange is from Mariner 10. And the altitude distributions are very similar, but Messenger deduced a factor of about 2 more hydrogen. And the reason we think is because Messenger had a smaller slit, and Mariner 10 had a very, very big slit, and probably averaged in a lot of area that really had no hydrogen. One thing that makes it difficult to reduce Lyman alpha observations is that there's the interplanetary hydrogen is the background. You have to know what that is to subtract it. And that's difficult. So helium there was an upper limit reported by Mariner 10, which is probably very much too large. So helium-4 is from the solar wind, and helium-3 is endogenic. It's primordial, both at the moon and Mercury. Benna estimated 10% of the helium is helium-3 at the moon, and it's been estimated that 15 to 20% is endogenic at Mercury. So similar. One thing that surprised me was that researchers don't think that helium is thermally accommodated at Mercury, whereas it is at the moon, and that could be because of the difference in the surface temperatures. So helium, as I said, it comes from the solar wind, and it's been shown to be correlated with the alpha particle flux, as you would expect. So the red line is the alpha particle flux, and the squares are LRO measurements, and the diamonds are from LADI, and they agree fairly well. So when I was working on this talk, I found this paper by Jasper Casper, can't remember his first name, but you almost always read that the helium abundance is 4% of the hydrogen in the solar wind, and you can see here that that's not true. It's about the peak of the distribution is about at 4% for the solar maximum, but at solar minimum, your helium is more like less than 1%. So this is a really astounding variation. And it's also actually found to be a function of solar wind speed. So that's important because the sputtering efficiency of helium is much greater than the sputtering efficiency for protons. And even your heavy ions in the solar wind vary quite a lot, and their sputter efficiency is like orders of magnitude more than for hydrogen. So what their fraction is in the solar wind is really important. So for argon, we had an upper limit from Mariner 10, but it's really a very high upper limit. Argon 40 is, of course, endogenic at the moon, and that's because it's a radiogenic byproduct of potassium 40. And it's often bursty, it's related to moonquakes, whereas argon 36 is of solar wind origin. And you can see from the curve here that that argon will condenses actually on the surface at night, and then it evaporates at sunrise, and then will bounce around the day side until the dusk, and then it starts condensing again. And it's interesting that if you look at the Laddie measurements, which are, whoops, went too fast. At any given particular time of day, the argon is fairly constant. But if you look at the argon as a function of selenographic longitude, you get a peak right above what's called the creep soil. Creep stands for potassium, rare earth elements, and phosphorus. And the bright red region there is a region of creep. And over creep, then you see a sudden increase in argon, which is really quite interesting. So neon is an interesting story. There was an instrument, a mass spec placed on the moon by Apollo 17, and it was called LACE. And Hodges published that the neon surface density was 4.4 times 10 to the 5. Then in 2015, Benna published that neon density is 3.5 times 10 to the 4. And then in 2013, Cook et al., and that was based on LAMP on LRO. And it was another order of magnitude down. And then I reanalyzed the LACE data and got a number consistent with Cook. And the reason for all of this is because this is a mass spectrometer. Neon mass is 20, fluorine mass is 20. And so we think that the mass 20 is contaminated. But it also has implications for the lifetime of neon on the surface of the moon. If the Benna number is correct, then the lifetime of neon is 100 days, which is the photoionization lifetime. And if my number and Cook's number is correct, the lifetime of neon on the moon is 4.5 days, which means there are additional escape processes, which could be impact vaporization, or sputtering, which I see no reason to believe that ionization is the only loss process. So there was an upper limit for neon from Mariner 10 at Mercury. FIPS is in the process of trying to separate neon from the oxygen group. They don't have really good mass resolution, but they're trying to tease that out. So neon will probably be measured by Bepi Colombo, probably by Strophio, possibly by Phoebus, the UV instrument. So the first thing that was measured by masks at Messenger was the tail of the escaping atoms. And we routinely looked at magnesium, calcium, and sodium. But our first observations, we immediately saw that these atoms, these different species are very different in their the way that, you know, they're seen. Calcium is almost always and consistently seen centered at the equator. In fact, it's centered at the dawn side. Magnesium is the least concentrated, whereas sodium is often seen at high latitudes. So they all have their own exosphere with its own distributions. And so what are we looking at? We're looking at resonance scattering, emission lines, and the reason we've been able to observe sodium from the ground is because it has enormous efficiency. We call it the G value. Just the whoppingly big emission lines. And they're easy to see from the ground, from the Earth, because they're seen in the visible region of the spectrum. So the other thing about emission lines is that the G value is a function of the distance of the atom or the body that it's on from the sun, but also the heliocentric radial velocity, which causes the Doppler shift. And so there's a huge variation in the G value as a function of radial velocity. So at perihelion and aphelion, where your radial velocity is near 0, your G value can be down here about 5. And then at higher Doppler shifts, a velocity of plus or minus 10 kilometers per second, your G value can be as high as 40. But one thing, when I made these plots, I didn't think about the fact that with radiation pressure, you're being accelerated at even higher velocities relative to the sun. So I then had to extend these curves farther out. So you can see that it's often been seen that there's a seasonal repeatability of the sodium exosphere, but in my opinion, you know, this is not properly reduced because a lot of the variation you see here is just the G value. But if you subtract out the G value, you see that there is variation on top of this seasonal variation. So G value is important, and you need to correct for that. So you can see sodium. The sodium that we see is inside of the solar Fraunhofer line, and that's why we have this big variation. Magnesium, the magnesium line, is not inside of the Fraunhofer line, and so it's not symmetric with respect to plus and minus Doppler shift, and that makes it very asymmetric with respect to the true anomaly of Mercury. And the other thing, this is calcium. Calcium is inside of a, you know, there's a calcium, huge calcium line in the solar spectrum. So what I wanted to point out is that, of course, the G value is very small at aphelion, and that means that the uncertainty in the observation is very large there. So I modeled these data. These are calcium at Mercury, and I modeled it using impact vaporization, as Mercury not only has an eccentric orbit, but it has an inclination relative to the interplanetary dust disk. And so if you take a model of the dust disk and you can model how much dust is impacting on the Mercury. And the model shows that you should get a calcium that follows the red curve, except along this green line here from dust. And there's this huge increase there. And we found out that that particular area is where Comet Encke's dust trail crosses Mercury's orbit. And, you know, I thought this is just the coolest thing. You know, you can see from the data where you're crossing the interplanetary dust disk and where you're crossing Encke's dust trail. So we also found out that calcium in Mercury's exospheres is extremely hot. We knew this from ground-based observations we took from the Keck. And from the scale height, we knew that calcium was at least 20,000 Kelvin. Any temperature above that doesn't really affect the scale height because it's just escaping. But Matt Berger deduced that the temperature of calcium is 70,000 Kelvin. But of course, it can't be that hot. It has to be non-thermal. And we think that the calcium is formed as some kind of a molecule, and then this is a model based on Berezhnoy's work, and he showed depending on the temperature of the fireball, you would have different molecules, and then these molecules would break up and form hot calcium and hot oxygen. In fact, you see a hot oxygen corona at Mars as well. And so this seems to be happening throughout the solar system. So magnesium is interesting in that we showed that the magnesium in the exosphere is very much correlated with the magnesium on the surface. The magnesium is very much non-uniform. As you see in the central panel, the red is in an enhanced region of magnesium. And because Mercury is in a 3-2 spin orbit resonance, every other year, we're looking at one side of Mercury, and the next year we're looking at the other side. So on the left side panel, then you see every other year. The first year you see more magnesium. That's when we're over this magnesium rich region. The next year you see less when we're over the magnesium poor region. And that shows that the exosphere is directly sourced from the surface. That may sound obvious, but it's only true, I mean, if the magnesium doesn't completely travel all the way around the planet. So we also saw what we call weakly emitting species. And we actually looked for aluminum and iron from the Keck, and we saw them, but not every year. And people thought, well, maybe we just didn't have the sensitivity or something. But it turns out we don't see these species every year from orbit either. And we think that these species might actually be also correlated with Comet Encke. And the other interesting thing here is you see the calcium plus doesn't peak at the surface. It peaks at about 350 kilometers from the surface. That means that it's sourced from neutral calcium, and then so it's one thing about calcium is it has a very rapid photoionization time, and so that's why it's becoming photoionized pretty close to the surface. And alumina also, I mean, it isn't dropping off from the surface, which means that it must have a source in the exosphere itself, probably from aluminum oxides. So sodium is really complicated, and the literature includes papers which name the major source of sodium to be thermal vaporization and PSD, which was from LeBlanc and Johnson, thermal vaporization from Gambarino, micrometeoritic bombardment from Pokorny, or sputtering from Orsini. So people don't agree on even what the most important source process is. So I wanted to point out some really interesting things about radiation pressure. Radiation pressure turns the tail upside down. And what I mean by that is if you have a sodium atom and it is ejected, say from sputtering at the northern cusp, you can see the orange dotted line, and the sodium, it starts following a normal trajectory around the planet in the shadow where it's not getting radiation pressure. But as soon as it starts getting radiation pressure, it starts being accelerated anti-sunward down the tail. But the sodium that you see in the tail in the southern hemisphere actually came from the north, and the opposite is happening from the sodium that's desorbed in the south. So I think that's just kind of a cool fact. Okay, so this is about the moon again. So on the right, you see scale height observations that I took with a coronagraph that we built and observed the moon. And on the left, you see observations from LADI. And one thing I wanted to point out is that what I'm showing here is that the scale height, or the temperature, increases from noon to morning, and it also increases again from noon to dusk. And you see here the temperature. A lot of people, you'll read in the literature, the temperature of sodium is 1200, and that's from PSD. But it actually, when the moon is in the magnetosheath or magnetosphere, the temperature increases, and you'll see on the right the column abundance here. This is 7 a.m., but it's also correlated with the time when the Artemis spacecraft measured the largest proton flux to the surface of the moon that was recorded, and we got the highest column abundance. So there's definitely a correlation, and they see this also with LADI when you get these right, the red, that's magnetotail exit, the blue is magnetotail entry, and what this region is the magnetosheath, and that's a region where you get a lot of turbulent ions from the solar wind that are entrained into the magnetosheath, and this is where you get the highest flux onto the surface of the moon. Okay, so you've probably all heard about water on the moon. This is an LRO lamp image that shows surface water in permanently shadowed craters. One thing that you notice is that the permanently shadowed craters some of them are full of surface water, some of them aren't. And on the right, you see just a cartoon of possible forms and scales of lunar polar volatility deposits. And what we don't know is how much subsurface water there is. One thing I didn't put on is at Mercury, we know that the polar permanently shadowed craters are full of water. And at Mercury, they're probably very deep, pure deposits of water. At the moon, you don't see that kind of a radar echo, which you would see with pure water. So we don't know really how deep the water is on the moon and how much water there is. Although there's been a lot of press about water on the moon. And there was a recent report by Casey Hannibal where she actually saw the 6-micron feature of water, which is a definite measurement of water on the moon, but we still don't know how much there is. One really interesting observation was phenomena called hollows. These are depressions. They don't have rims, so they're not impact features. They're probably features where volatiles desorbed and the soil just fell away. But around these areas, there's a very bright something that's very bright material, and that's presumed to be sublimated out of the hollows. And so it's been proposed many times that these features are a sulfur salt, and that we might see a sulfur exosphere. But of course, the G value of sulfur is 10 to the minus 6. So we had no chance of seeing it in the exosphere. So we also have a problem with oxygen. There was an upper limit from Mariner 10, but masks did not see oxygen. There was a very small upper limit, I think like 25 Rayleighs. So why don't we see oxygen at Mercury? Is it in molecular form? Is it ionized? Is it a negative ion? You know, oxygen is highly electronegative, so could be negative ion. BIPS was not set up to look for negative ions, although you could do that. Is it not easily sputtered? People say it should be. Is there a hot oxygen exosphere and it's just escaping and it's there's not enough to see? Or is the surface simply highly reduced and there isn't a lot of oxygen? So these are questions that maybe Beppe Colombo could investigate. So I'm going to show some things that I showed for EPSC, and this is the effect of seeing on ground-based observations. And it's often been seen that there are high latitude enhancements in sodium images. And what I'm showing is that you can produce high latitude spots even with a completely uniform exosphere. And what I'm going to compare is observations from ground-based telescopes taken by Mangano et al. And simulated images from a completely uniform exosphere. So I can simulate an equatorial peak with a uniform exosphere and 2.5 arc seconds of seeing. I can simulate a wide peak with 1.25 arc second of seeing. And what you're seeing is limb brightening. I can simulate a connected double peak with 1.75 arc second seeing, and I can simulate high latitude peaks with 2 arc second seeing by doing stretching the image to enhance the variation. So I think what I'm trying to say is that you need to be careful about your observations, that they're properly reduced and that you understand what you're looking at. We can't simulate asymmetric peaks with a uniform exosphere. And these are often seen, and it was proposed, it was found by Messenger, the MAG instrument, that you have an offset dipole, and that would mean that the cusp in the southern hemisphere is larger in area than in the northern hemisphere. And these differences are often seen. So I just wanted to throw that out, that seeing is often, could confuse you. And I just want to acknowledge the masks team from the Messenger mask UV spectrometer team. Ground-based observations have been done by many people over many years. And the lunar data from LACE, LRO, LADI, SOFIA, ground-based telescopes and coronagraphic observations, and co-authors who helped me with the impact vaporization. And thank you very much for your attention.
I have two questions. One is that I haven't got very clear from the beginning this exospheres. How much of it is neutral and how much ion is? It's not very clear to me. The second question is, among these subjects you talked about, these are interesting subjects, but if you want to identify something that's still missing or some instrument that could be interesting, which one would you think is or which kind of experiment you would look for? Yeah, thank you.
Well, there are two things. I think, as I mentioned, the oxygen, I think it's important to tie down how much oxygen there is. Also, as far as ions are concerned, I think you're going to hear about ions from the next talk, Jasper Halakas. He's the plasma guy, but so what I've been talking about is mostly neutrals, except that I mentioned calcium plus. Of course, you'll see more neutrals than ions, but it's interesting that the FIPS instrument, it's a fast imaging plasma spectrometer. They saw sodium ions on the dusk side and protons on the dawn side. I believe that's right, and that has to do with the convection electric fields in the magnetosphere. So the ions, they aren't seen where they're produced any more than the neutrals are. Yeah, FIPS did see from mass 1 to 50, but their mass resolution was increasingly worse as the mass increased. So they, in fact, even for, they had the water group because they couldn't distinguish oxygen, OH, and H2O ions. So a lot of what so like even the sodium ion and magnesium ion, they have the same mass relative to their mass resolution. But they, yeah, if you're interested in ions, there are a lot of papers by Jim Raines and his group. And Jasper is probably going to talk about that.
Okay. Any further questions?
Hi,
Come on. Who's this?
and Zhongyi.
Okay, go ahead.
So you mentioned the mercury. I mean, there are some atom or molecular the detection they are from the cometary orbit. So so how about the moon? Do we know is there any contamination from the meteor shower or the cometary orbit?
Yes, the LADI measurements did show correlations with meteor showers. That's been seen for, for actually a number of decades. Different observations find that the lunar sodium is enhanced in meteor showers, and the tail is enhanced in after a shower because you have more escaping. In fact, the potassium radiation pressure is much faster than sodium, and so you get a very long sodium tail and a long potassium tail from radiation pressure. And you can see these long tails, especially after a meteor shower. And the Haunches, is this guy named Haunches. It's spelled with a J. He studied impacts at the moon, and of course, your ram direction is where the moon is plowing into the interplanetary dust, and so you'll see. And also, the Jamie Zalay published really nice papers showing that the impact vaporization at the moon is centered between 6 a.m. and say 9 a.m. depending on the exact time of year, because that's where your ram direction is between the moon and the interplanetary medium. So that's a whole area of study in itself. It's very interesting.
Okay, any further questions? Any more questions from other places? If not, Rosemary, thank you so much. And we'll hear you again next time, all right? And have a good night's sleep.
Okay, and as I said, the study of the lunar exosphere there's a lot more than I was able to talk about in a half hour. As your students pointed out, the impact vaporization is variable, and of course, you're running through the meteor showers are actually they're from comet dust tails as well. So just like the Comet Encke tail impacting Mercury, the comets have tails and they impact the moon at various times. The Leonids and the Geminids are two of the big ones that impact and cause a lot of impact vaporization at the moon. So that's absolutely true, and they have different radiants too. So one meteor shower might impact around the equator, and another one would impact in the polar regions. So depending on which meteor shower it is, the radiant, it could be quite different.